There's an image burned into your brain from childhood, and tonight we're going to burn it out. The solar system. The sun glowing at the center. 8 planets strung out in a tidy line. Everything sitting flat on a single invisible surface, like coins on a tabletop. Clean, orderly, familiar, wrong. The solar system was never flat. And the moment you ask what's actually above it and below it, you step into a question so strange it might follow you into your sleep. Because in space, there is no up, there is no down. Those directions that feel as natural as breathing simply do not exist out there. And yet, something is above the planets. Something is below them. And what stretches in every direction around our solar system is so much larger, so much stranger than most people ever stop to consider. Let's start with that picture. You know exactly the one. The sun at the center, bright and commanding, and the planets arranged outward in a neat procession. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all orbiting on the same level, like beads on a single wire. You've seen this image in textbooks, on classroom walls, in documentaries, on the back of cereal boxes. It's one of the most reproduced diagrams in the history of science, and it has done something to your brain you probably never noticed. It has convinced you that the solar system is flat, that everything of consequence exists on one plane, that if you pointed a spaceship straight up, perpendicular to the orbits of the planets, you'd be leaving the action almost immediately, flying away from the disk into empty space where nothing interesting happens. This idea is so deeply embedded that most people never question it, but it deserves to be questioned, because that flat diagram isn't showing you the solar system. It's showing you a carefully filtered slice of it and hiding almost everything else. So, why does the solar system look flat in the first place? Is it just an artistic choice? A convenience of illustration? No, it reflects something physically real. And to understand it, we have to go back about 4,600,000,000 years, to before the sun existed, before the planets existed, before there was anything recognizable as our solar system at all. What existed instead was a cloud, an enormous, slowly drifting cloud of gas and dust floating in interstellar space, mostly hydrogen and helium, the lightest elements, with traces of heavier atoms woven in: carbon, oxygen, silicon, iron, gifts from earlier generations of stars that had lived, burned out, and scattered their material across the galaxy in supernova explosions. This cloud is what astronomers call a molecular cloud, or, when we're talking about the one that became our home system, a solar nebula. It stretched across light years of space, and for a long time, it simply existed, held in rough balance between its own gravity pulling inward and the internal pressure of the gas pushing out. Then something disturbed it. Maybe a nearby supernova sent a shockwave rippling through the cloud. Maybe a passing star gave it a gravitational nudge. Whatever the trigger, part of the cloud began to collapse under its own weight. And as it collapsed, something crucial happened. It started to spin. It was probably already rotating slightly. Almost everything in the universe carries some faint trace of rotation. But as the cloud contracted, that rotation amplified dramatically. This is the same physics that makes a figure skater pull in her arms and suddenly spin faster. Conservation of angular momentum. The smaller the cloud got, the faster it turned. And here's the key to understanding why the solar system looks the way it does. a spinning, collapsing cloud naturally flattens out. Think of tossing pizza dough and spinning it. The spin flings material outward along the plane of rotation, while gravity pulls it inward toward the center. The result is a disk. The same process happened to the solar nebula. The collapse produced a spinning disk of gas and dust with a dense concentration at the center, the young sun, and a broad rotating disk around it, the protoplanetary disk. Everything that followed happened inside that disk. Dust grains collided and stuck together. Pebbles formed. Pebbles became boulders. Boulders became kilometer-scale objects called planetesimals, which collided and merged into protoplanets, which eventually became the 8 worlds we know. Because they all formed from the same flat rotating disk, they inherited its geometry. They orbit in roughly the same plane because that plane was their birthplace. Astronomers call this plane the ecliptic, defined specifically by Earth's orbit around the sun. It's the baseline, the zero line, the reference surface that the familiar flat diagram is actually showing you. And for the major planets, it works reasonably well. They really do orbit close to the ecliptic. The diagram is capturing something true about their geometry. But here is where things start to get more interesting. The planets orbit roughly in the ecliptic plane, but not exactly. Every planet's orbit is tilted slightly, by an angle astronomers call the orbital inclination, measured in degrees. 0 degrees means perfect alignment with the ecliptic. 90 degrees would mean a completely perpendicular orbit, looping straight over the sun rather than circling around it. The actual numbers are small, but they're not 0. Mercury, the closest planet to the sun, has an inclination of about 7 degrees. That's the highest of any major planet. 7 degrees may not sound dramatic, but Mercury orbits the sun at an average distance of roughly 58 million kilometers. At that distance, a 7-degree tilt means Mercury can reach heights of about 7 million kilometers above or below the ecliptic, nearly 10 times the diameter of the sun itself. The flat diagram has already told you a lie, and we haven't even left the inner solar system yet. Venus tilts about 3.5 degrees. Earth, by definition, sits at 0. The ecliptic is defined by Earth's orbit. Mars tilts about 1.85 degrees. Jupiter about 1.3. Saturn 2.5. Uranus less than 1 degree. Neptune about 1.8. None are exactly flat. The solar system, even at its most orderly, is a thin disk with planets gently wobbling above and below the central plane, not a perfectly level surface. Why didn't they form with perfectly 0 inclination? Because the early solar system was not a quiet place. As protoplanets grew, their gravitational fields reached out and pulled on everything nearby. Close encounters tilted orbits. Planets migrated inward and outward through the disk, and those migrations changed their inclinations. Jupiter, with its enormous mass, exerted a gravitational influence on the entire system, and the solar system may have passed through a period of dramatic instability. The Nice model, named for the French city where it was developed, in which the giant planets briefly reshuffled their positions, scattering smaller objects across the system and adjusting orbital tilts throughout. The small inclinations we see today are fossil evidence of that violent youth. The chaos eventually settled, but it left its fingerprints behind. Now, the ecliptic plane itself is worth understanding clearly, because everything that follows depends on it. It is not a physical surface. There is no wall, no floor, no membrane. It is a mathematical construct, the flat plane traced out by Earth's path around the sun, extended outward in all directions, like an invisible, infinitely large tabletop. When astronomers say something is above the ecliptic, they mean it lies on the north side of this surface. When they say below, they mean the south side. North here is defined by a simple rule. Curl the fingers of your right hand in the direction Earth orbits the sun, and your thumb points ecliptic north, roughly toward the constellation Draco. But here is something important to hold on to. This is a choice, a human choice. There is nothing physically special about the ecliptic plane compared to any other plane you might define in space. We use it because Earth is our home, and Earth's orbit is our natural reference. But if you lived on Mars, you'd use a plane tilted almost 2 degrees relative to ours. If you lived on Mercury, your reference would tilt 7 degrees. The question, what is above the solar system, only has meaning once you decide what above means. And that decision is ours, not the universe's. This matters more than it might seem at first, because there is another reference plane astronomers use, the invariable plane of the solar system. This is defined not by Earth's orbit, but by the total angular momentum of everything in the solar system. Every planet, every moon, every comet, every drifting particle of dust. Because Jupiter holds so much of the solar system's angular momentum, so massive, orbiting so far from the sun, the invariable plane lies close to Jupiter's orbital plane, tilted about 1.6 degrees relative to the ecliptic, a small difference, but a real one. And in some ways, a more physically meaningful reference, because it accounts for the whole system rather than just one planet's path. The fact that the ecliptic and the invariable plane are so close to each other tells us something reassuring. The solar system really is quite flat, at least in the region where the major planets orbit. Both reference frames give roughly the same answer. The flat diagram, limited as it is capturing something genuine, but for the planets only. The moment you look beyond them, the flatness begins to crack. And then, as we move outward into the solar system's darker, more distant regions, it shatters completely. Here's a way to feel the true dimensions of what we're dealing with. The 8 planets orbit the sun at distances ranging from about 58 million kilometers for Mercury to about 4,500,000,000 kilometers for Neptune. That's a span of roughly 4,400,000,000 kilometers from innermost to outermost planet. But the maximum height any major planet reaches above or below the ecliptic is only about 7 million kilometers, and that's Mercury, with its unusually high inclination. Most planets stay far closer to the plane than that. Do the math. The disk of planets is approximately 300 times wider than it is thick, 300 to 1. If you scaled the whole planetary region down to the size of a compact disk, the thickness would be comparable to a single sheet of paper. The flat diagram earns its flatness for the 8 planets. It is, in that narrow sense, an honest representation. The key phrase is, for the 8 major planets. The solar system contains far more than 8 planets. It is filled with dwarf planets, asteroids, comets, and billions of small icy bodies, and many of them do not follow the rules of the flat disk at all. These are the objects that reveal the solar system's hidden dimension. A vertical dimension the flat diagram erases entirely. And as we move outward, past the familiar worlds, into the cold outer reaches of the solar system, that hidden dimension does not just become visible, it becomes impossible to ignore. Remainder. Time codes. Removed. Even within the region of the major planets, there are hints that the solar system is more three-dimensional than it appears. The asteroid belt, which sits between Mars and Jupiter, contains millions of rocky objects. Most of these orbit roughly in the ecliptic plane, but their inclinations are generally larger than those of the planets, while the planets have inclinations of at most 7 degrees. Asteroids in the main belt can have inclinations of 20 degrees or more. Some asteroids orbit on paths that take them well above and below the ecliptic, looping high over the plane of the planets before diving back down and passing through it again. Pallas, one of the largest asteroids in the main belt, has an orbital inclination of about 34.8 degrees. That's enormous compared to the planets. Pallas doesn't stay anywhere near the flat disk that the planets occupy. Its orbit takes it far above and below the ecliptic, reaching heights of hundreds of millions of kilometers above and below the plane. If you included Pallas in the standard flat diagram of the solar system, it would be way off the page, floating above or below the neat line of planets. But Pallas is almost never shown in those diagrams, precisely because it doesn't fit the flat picture. The diagrams exclude objects that break the flatness, which reinforces the illusion that the solar system is flat. This is a pattern you'll see again and again. The flat diagram of the solar system is a filtered view. It shows you the objects that happen to orbit near the ecliptic and hides the ones that don't. It's like taking a photograph of a city, but only including the buildings on one street. You get a picture that suggests the city is a straight line, when in reality, it extends in all directions and has far more structure than one street can show. The solar system is the same way. The ecliptic plane is one street, but there are objects above and below that street, objects that reveal the solar system's true three-dimensional nature. Another fascinating example is the dwarf planet Ceres, the largest object in the asteroid belt. Ceres has an inclination of about 10.6 degrees, not as dramatic as Pallas, but still significantly higher than any of the major planets. Ceres moves above and below the ecliptic by tens of millions of kilometers during each orbit. Vesta, another large asteroid, has an inclination of about 7.1 degrees, similar to Mercury. These are substantial tilts that would be clearly visible if you could watch these objects from outside the solar system. The point here is that the flat diagram is a gross simplification even within the inner solar system. It works well enough for the 8 major planets, but it fails for asteroids, and it will fail even more spectacularly as we move outward to the more distant and exotic regions of the solar system. Let's talk about another subtlety that the flat diagram hides. The planets don't just orbit in slightly different planes. Their orbital planes also precess. Precession is a slow wobble, like a spinning top, that gradually changes the direction its axis points. Each planet's orbital plane slowly rotates over time, driven by the gravitational pull of the other planets, especially Jupiter and Saturn. This means the ecliptic plane itself isn't fixed. It shifts over thousands of years. The amount of shift is small, but it's real. Over tens of thousands of years, the orientation of the planetary orbit slowly changes, and with it, the definition of above and below changes too. This precession is another reminder that the flat diagram is a snapshot, not a permanent truth. The solar system's geometry is dynamic. The planes of the orbits are not locked in place. They shift, they wobble, they evolve. The flatness you see today is a momentary arrangement, a frozen instant in a slow gravitational dance that's been going on for billions of years and will continue for billions more. Even the sun itself contributes to the three-dimensional complexity. The sun isn't a stationary point at the center of a flat disk. It has its own motion. The sun orbits the center of the Milky Way galaxy at a speed of about 230 kilometers per second. As it moves, it carries the entire solar system with it. But the sun doesn't move in a perfectly flat orbit around the galaxy. It bobs up and down through the galactic plane, oscillating above and below the midplane of the Milky Way over a period of about 60 to 70 million years. This means the entire solar system, ecliptic, plane, and all, is itself moving up and down relative to a larger reference plane, the plane of the galaxy. We'll explore this in much more detail later, but for now, the takeaway is that even the frame of reference we use to define above and below the ecliptic plane is itself tilted and moving within a larger cosmic structure. So, where does all this leave us? We start with the familiar flat diagram of the solar system, and we've begun to peel back the layers of simplification. The diagram is useful. It captures something real about the geometry of the planetary orbits. The 8 major planets really do orbit roughly in the same plane, a consequence of their formation from a flat protoplanetary disk. But even among the major planets, there are small but real inclinations that take them above and below the ecliptic. In the asteroid belt, those inclinations become much larger, and the ecliptic plane itself is not fixed or absolute. It's a human-defined reference frame that shifts over time and is tilted relative to larger structures in the galaxy. The flat diagram is a starting point, not an ending point. It shows you the solar system's skeleton, the basic framework of planetary orbits that defines its large-scale geometry. But the full solar system is far richer, far more complex, and far more three-dimensional than that skeleton suggests. The objects that break the flatness, the asteroids with steep inclinations, the comets that come screaming in from bizarre angles, the distant icy bodies that orbit in planes, nothing like the ecliptic. These are the objects that reveal what actually lies above and below the neat picture you've always been shown. And as we move outward from the planets, past the asteroid belt, past the orbits of the giant planets, into the cold and distant reaches of the outer solar system, the flat picture doesn't just become incomplete, it becomes almost meaningless. Because out there in the dark spaces beyond Neptune, the solar system opens up into something the textbook diagram never prepared you for. Something vast, something spherical, something that extends above and below the planetary plane by distances so enormous they stretch nearly halfway to the nearest star. The flat disk of planets that you thought was the solar system is only the thinnest innermost layer of a structure far larger and far more three-dimensional than anything the standard diagram could ever show you. Now, let's leave the familiar territory of the 8 planets and travel outward, past Neptune, into the cold, dark frontier of the outer solar system. Because this is where the flat picture you've carried in your head your entire life doesn't just bend, it shatters. Everything we talked about so far, the small orbital tilts of the planets, the modest inclinations of certain asteroids, those were gentle hints that the solar system has a vertical dimension. What comes next is not a hint, it's a declaration. The outer solar system is a place where objects orbit at steep, dramatic angles, where the ecliptic plane becomes almost irrelevant, and where the true three-dimensional architecture of our solar system finally reveals itself. The first sign that something strange is happening comes from an old friend, Pluto. For 76 years, from its discovery in 1930 until its reclassification in 2006, Pluto was considered the ninth planet. School children memorized it. Posters included it. It was the last stop on the flat diagram, sitting at the edge of the planetary line, a small frozen world at the end of the row. But Pluto was never comfortable in that lineup. It never really fit, and one of the biggest reasons it didn't fit is its orbit. Pluto's orbital inclination is about 17 degrees relative to the ecliptic. That's more than twice Mercury's inclination, which is the highest among the 8 major planets. 17 degrees is a dramatic tilt. It means that Pluto's orbit takes it far above and below the plane where the other planets travel. At its greatest distance from the ecliptic, Pluto can be more than 1,200,000,000 kilometers above or below the flat disk of the planets. To put that in perspective, that's more than 8 times the distance from Earth to the Sun. Pluto doesn't just wobble slightly above and below the ecliptic. It soars far beyond it, looping high above the planetary plane on one side of its orbit, and then diving deep below it on the other side. If you could watch Pluto's orbit from the side, looking at the solar system edge on, you would see the 8 planets tracing nearly flat paths, barely deviating from the central plane. And then you'd see Pluto's path slicing through that plane at a steep angle, like a hula hoop leaning against a table. Pluto crosses the ecliptic twice during each of its 248 Earth-year orbits, spending half its time above the plane and half below it. The standard flat diagram can't show this. It has no room for an object that spends most of its time far from the ecliptic, so the diagram either excludes Pluto entirely or places it on the flat line with everything else, hiding its true orbital geometry. But Pluto's orbit is strange in another way too. It's highly eccentric, stretched into an elongated ellipse rather than being close to a circle. At its closest approach to the Sun, called perihelion, Pluto comes within about 4,400,000,000 kilometers, actually inside Neptune's orbit. At its farthest point, aphelion, it's about 7,400,000,000 kilometers from the Sun. This huge variation in distance, combined with the steep inclination, means Pluto's path through space is nothing like the neat circular orbit shown in textbook diagrams. It's a tilted, stretched loop that occupies a very different region of space from the other planets. And Pluto was just the beginning, because Pluto, it turns out, is not alone out there. It's one member of a vast population of icy objects beyond Neptune, and many of them have orbits that are even more inclined, even more eccentric, and even more dramatic than Pluto's. This is the Kuiper Belt, and its discovery fundamentally changed our understanding of the solar system's shape. The Kuiper Belt is a region of space extending from roughly the orbit of Neptune about 30 astronomical units from the Sun to about 50 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. It's a vast ring of icy bodies, remnants from the formation of the solar system that never coalesced into a planet. The existence of the Kuiper Belt was predicted long before it was confirmed. In 1951, astronomer Gerard Kuiper suggested that a belt of small icy bodies might exist beyond Neptune. But it wasn't until 1992 that astronomers David Jewett and Jane Liu discovered the first Kuiper Belt object other than Pluto, a small body designated 1992 QB1. Since then, more than 2,000 Kuiper Belt objects have been discovered, and astronomers estimate that the belt contains hundreds of thousands of objects larger than 100 kilometers in diameter, and possibly trillions of smaller ones. Now, here's what matters for our story. The Kuiper Belt is not flat. It's much thicker and more three-dimensional than the planetary region of the solar system. While the 8 planets orbit within a disk that's only a few degrees thick, the Kuiper Belt contains objects with a wide range of inclinations. Some orbit close to the ecliptic, but many don't. The overall structure of the Kuiper Belt is more like a thick donut than a thin disk. Objects within it can have inclinations of 5, 10, 20, or even 30 degrees or more. Astronomers divide Kuiper Belt objects into several categories based on their orbital characteristics, and each category tells us something different about the solar system's three-dimensional structure. The classical Kuiper Belt objects, sometimes called cubewanos, after the first one discovered, orbit between about 42 and 48 astronomical units from the Sun in relatively circular orbits. These objects have a range of inclinations that divides them into 2 populations. The cold, classical population has low inclinations, typically less than 5 degrees. These objects orbit close to the ecliptic, almost like a thin extension of the planetary disk. But the hot, classical population has much higher inclinations, up to 30 degrees or more. These objects were likely scattered into their current orbits by gravitational interactions with Neptune during the early solar system. The fact that there are 2 distinct populations within the same region of space, one flat and one puffy, tells us that the Kuiper Belt has a complex vertical structure. It's not a single flat ring. It's a layered structure with a thin component embedded within a thicker one. Then there are the resonant Kuiper Belt objects. These are bodies whose orbital periods are in a simple ratio with Neptune's orbital period. Pluto is the most famous example. Its orbital period is in a 3:2 ratio with Neptune's, meaning Neptune goes around the Sun 3 times for every 2 times Pluto does. This 3:2 resonance keeps Pluto and Neptune from ever colliding, even though their orbits cross. Other resonant populations exist at different ratios. Objects in these resonances can have a wide range of inclinations, from nearly flat orbits to steeply tilted ones. The resonances can actually protect objects at high inclinations from being ejected from the solar system, allowing them to survive on tilted orbits for billions of years that would otherwise be unstable. But the most dramatic departure from the flat picture comes from a population called the scattered disk. These are objects that have been flung onto highly eccentric and highly inclined orbits by gravitational encounters with Neptune. Scattered disk objects can have orbital distances ranging from about 30 astronomical units at their closest to hundreds, or even thousands, of astronomical units at their farthest. Their inclinations can be extreme. Some scattered disk objects orbit at inclinations of 40 degrees or more. Eris is the most famous scattered disk object, discovered in 2005 by astronomer Mike Brown and his team. Eris was the discovery that ultimately led to Pluto's reclassification as a dwarf planet. Eris is actually slightly more massive than Pluto, though slightly smaller in diameter. Its orbital inclination is about 44 degrees, nearly halfway to being perpendicular to the ecliptic. Eris's orbit takes it so far above and below the planetary plane that trying to include it in the standard flat solar system diagram would be absurd. At its maximum distance from the ecliptic, Eris can be billions of kilometers above or below the plane where the planets orbit. It spends most of its 559-year orbit far from the ecliptic, soaring above or diving below the flat disk that the textbook diagram shows. Eris's orbit is also highly eccentric. At perihelion, it comes within about 38 astronomical units of the Sun, just inside the outer edge of the Kuiper Belt. At aphelion, it's about 98 astronomical units away, more than twice Pluto's average distance from the Sun. This enormous orbit, steeply tilted and wildly stretched, occupies a volume of space that the flat diagram simply cannot represent. Eris is part of the solar system. It orbits the Sun. It's made of the same primordial material as the planets, but it lives in a completely different geometric reality from the one the flat picture shows. And Eris isn't even the most extreme example. There are scattered disk objects with inclinations exceeding 50 or 60 degrees. Some have orbits that take them so far from the ecliptic that they spend centuries at a time far above or below the planetary plane, invisible to surveys that concentrate their observations near the ecliptic. We've almost certainly only found a fraction of the scattered disk population. The objects we found are the ones that happen to be near the ecliptic when we looked. The ones far above or below the ecliptic at great distances from the Sun are extremely faint and extremely hard to find. The scattered disk could contain far more mass and far more objects than we currently know about. There's another population that pushes the three-dimensional nature of the solar system even further. These are called detached objects, or sometimes extended scattered disk objects. These bodies have orbits so distant that they're no longer significantly influenced by Neptune's gravity. Their perihelia, their closest approaches to the Sun, are far enough out that Neptune can't perturb them. Something else must have shaped their orbits. Maybe it was a passing star in the distant past. Maybe it was the combined gravity of many small perturbations over billions of years. Maybe it was the influence of a large undiscovered planet in the outer solar system, which some astronomers have hypothesized and dubbed Planet 9. Sedna is the most famous detached object. Discovered in 2003 by Mike Brown, Chad Trujillo, and David Rabinowitz, Sedna has one of the most extreme orbits of any known solar system object. Its perihelion is about 76 astronomical units from the Sun, far beyond Neptune's influence. Its aphelion is a staggering 937 astronomical units, roughly 140 billion kilometers from the Sun. Sedna takes about 11,400 Earth years to complete one orbit. Its inclination is about 11.9 degrees, relatively modest compared to Eris, but its enormous distance means that it occupies a vast volume of space far from the ecliptic. Another remarkable detached object is 2012 VP 113, which has a perihelion of about 80 astronomical units and a semi-major axis of about 265 astronomical units. Its inclination is about 24 degrees. These detached objects hint at a population of bodies orbiting in the deep outer solar system, well beyond the Kuiper belt, in orbits that can be significantly tilted relative to the ecliptic. They're the furthest confirmed members of the solar system before we reach the hypothesized Oort cloud, and they suggest that the transition from the relatively flat inner solar system to the spherical outer solar system is gradual, with inclinations getting larger and larger as you move outward. Now, let's talk about comets, because comets provide some of the most dramatic evidence that the solar system extends far above and below the ecliptic plane. There are two main types of comets, and they tell very different stories about the solar system's geometry. Short-period comets, those with orbital periods of less than 200 years, mostly come from the Kuiper belt and scattered disk. They tend to have relatively low inclinations, orbiting within about 30 degrees of the ecliptic. This makes sense because they were scattered inward from the Kuiper belt region, which, while thicker than the planetary disk, is still somewhat concentrated near the ecliptic. But there are exceptions. Halley's Comet, which has an orbital period of about 75 to 79 years and an inclination of about 162 degrees, is technically short period by its timing, but its retrograde orbit suggests it originally came from the Oort cloud rather than the Kuiper belt. An inclination greater than 90 degrees means the object orbits in the opposite direction from the planets. It's called a retrograde orbit. Halley's Comet orbits the Sun backward relative to the planets, and its orbit is tilted significantly from the ecliptic. Every time Halley's Comet visits the inner solar system, it's a vivid reminder that the solar system contains objects moving on paths, nothing like the neat prograde orbits of the planets. Long-period comets are even more revealing. These are comets with orbital periods greater than 200 years, sometimes stretching to millions of years. They come from much farther away, from the outermost reaches of the solar system. And here's the crucial point. Long-period comets come from every direction. Their orbital inclinations span the full range from 0 to 180 degrees. They come in from above the ecliptic, from below it, from every angle imaginable. Some orbit in the same direction as the planets. Others orbit backward. Their paths are essentially random in orientation. This is incredibly important for understanding what lies above and below the solar system. If long-period comets come from all directions equally, then their source, the reservoir from which they originate, must be spherical. It must surround the solar system in every direction, above, below, and all around, with roughly equal density in all directions. A flat disk source would produce comets that mostly come from near the ecliptic. Only a spherical source can produce comets arriving from every direction. This was one of the first and strongest pieces of evidence for the existence of the Oort cloud, the vast spherical shell of icy bodies that surrounds the entire solar system. But we'll talk about the Oort cloud in detail shortly. For now, the point is that comets demonstrate that the solar system is not a flat structure. Objects orbit the sun at every possible angle. The flat diagram shows you only the most orderly objects, the planets, which happen to orbit near the ecliptic. It hides the chaotic, tilted, three-dimensional reality of the outer solar system. Let me give you a way to visualize all of this. Imagine you're floating in space, far above the ecliptic plane, looking down at the solar system from the north. From this vantage point, you see the sun at the center and the 8 planets orbiting in nearly circular paths, all going in the same direction. It looks like the flat diagram, a set of concentric rings around a central point. Now, zoom out further. You start to see the Kuiper Belt, a broader, thicker ring beyond Neptune's orbit. Some objects in this ring are in the plane, but others are above and below your line of sight, their orbits tilted so they trace paths that loop above and below the planetary plane. The neat, flat picture is getting fuzzy around the edges. Now, change your vantage point. Instead of looking from above, look at the solar system, edge on. From this perspective, the planets form a thin line, a narrow band centered on the ecliptic, but the Kuiper Belt objects spread out above and below this line, forming a thicker band. And the scattered disk objects spread out even further, some orbiting at angles so steep they're nearly perpendicular to the planetary line. The neat, thin line of planets is surrounded by a diffuse cloud of objects that extends far above and below it. The solar system seen edge on is not a thin disk. It's a thin disk embedded within a much thicker, much more extended distribution of objects. And it gets even more dramatic. Among the more distant objects, there are a few that challenge our understanding of solar system formation entirely. In 2008, astronomers discovered an object designated 2008 KV42, nicknamed DRAC. It orbits the sun in a retrograde direction with an inclination of about 104 degrees. This means it's not only orbiting at a steep angle to the ecliptic, but going around the sun in the opposite direction from the planets. It was one of the first trans-Neptunian objects found to have a retrograde orbit. Its existence suggests that some outer solar system objects have been scattered so violently that their orbits have been completely flipped, turned upside down relative to the planetary plane. How does this happen? Gravitational encounters with the giant planets, especially Neptune, can gradually increase an object's inclination over millions of years. But to flip an orbit completely into retrograde requires extreme perturbation. Some models suggest that interactions with passing stars or the gravitational influence of the galactic tide, the combined gravity of all the matter in the Milky Way, can flip orbits over very long timescales. The galactic halo is a roughly spherical region surrounding the disk, extending tens of thousands of light years above and below the galactic plane. The halo contains old stars, many of them among the oldest in the galaxy, formed more than 10 billion years ago when the Milky Way was young. These halo stars are metal poor, meaning they contain fewer heavy elements than stars in the disk, because they formed before earlier generations of stars had enriched the galaxy's gas with heavy elements. The halo also contains globular clusters, dense spherical collections of hundreds of thousands of stars. About 150 globular clusters are known to orbit the Milky Way, scattered throughout the halo. Some are relatively close to the galactic plane. Others orbit at enormous distances, tens of thousands of light years above or below the disk. These clusters are ancient, typically 10 to 13 billion years old, and they trace the structure of the halo like ornaments on a Christmas tree, revealing its shape and extent. But the halo isn't just stars and globular clusters. It's mostly dark matter. The Milky Way's dark matter halo is thought to extend far beyond the visible stellar halo, reaching out to perhaps 600,000 light-years or more from the galactic center. This dark matter halo is roughly spherical and contains most of the galaxy's total mass. We can't see dark matter directly, but we can detect its gravitational effects. The way stars orbit in the outer parts of the galaxy, moving faster than they should, based on the visible matter alone, tells us that there's a vast invisible mass surrounding the galaxy, holding it together. So, if you traveled straight up from the galactic plane, you'd pass through the thin disk, then the thick disk, then the stellar halo with its old stars and globular clusters, then the outer reaches of the dark matter halo. The stellar density would drop rapidly once you left the disk. And by the time you were a few thousand light years above the plane, stars would be sparse. Tens of thousands of light years above the plane, you'd be in the deep halo, with only occasional old stars and globular clusters scattered through a vast space dominated by invisible dark matter. And beyond the dark matter halo, intergalactic space, the void between galaxies. This is the emptiest environment in the known universe. The density of matter in intergalactic space is extraordinarily low, roughly 1 atom per 10 cubic meters. It's not perfectly empty. There's a thin intergalactic medium, mostly ionized hydrogen, stretched across the vast distances between galaxies. But it's so sparse that for all practical purposes, it's a vacuum. In intergalactic space, looking back down at the Milky Way, you'd see our galaxy as a luminous disk with spiral arms, a bright central bulge, and a faint extended halo. The solar system would be completely invisible, an imperceptible dot on one of the minor spiral features. Earth would be beyond any hope of detection. Looking outward, you'd see other galaxies. The nearest large galaxy, Andromeda, visible about 2.5 million light-years away. The Magellanic Clouds, satellite galaxies of the Milky Way, visible as fuzzy patches. Dozens of smaller dwarf galaxies scattered around, some close, some distant. This is what lies above the solar system when you follow the direction to its ultimate conclusion. Start at Earth, travel perpendicular to the ecliptic, pass through the Oort cloud, enter interstellar space, continue upward, now perpendicular to the galactic plane, since the ecliptic is tilted relative to it. Pass through the galactic disk, rise into the stellar halo, continue into the dark matter halo, leave the galaxy entirely, enter intergalactic space, and eventually encounter other galaxies, other clusters, other superclusters. There's no ceiling, no boundary, no wall, just an endless expanse of space containing structures at every scale, from individual stars to galaxy clusters to cosmic filaments stretching billions of light years. But here's the crucial insight that ties everything together. There is no real above. There is no real below. These concepts are inventions of our terrestrial experience, products of living on the surface of a planet where gravity defines a clear and consistent down. In space, away from any single gravitational source, there is no preferred direction. There is no up, no down, no above, no below. There is only space, extending equally in all directions. When we talk about what's above the solar system, we're implicitly choosing a reference plane, usually the ecliptic, and defining above as one of the two directions perpendicular to it. But this is a choice, not a physical reality. We could just as easily use the galactic plane, which would give us a different above, or the invariable plane of the solar system, which would give us yet another slightly different above. Or we could orient ourselves relative to the cosmic microwave background, the faint radiation left over from the Big Bang, which fills the universe almost perfectly uniformly in all directions and has no preferred plane at all. The concept of direction is relative in a deep physical sense. Einstein's general theory of relativity tells us that space and time are curved by mass and energy. There's no absolute coordinate system painted on the fabric of space. Directions only have meaning relative to something, relative to the local gravitational field, relative to a rotating body, relative to a chosen reference frame. In the solar system, we choose the ecliptic. In the galaxy, we choose the galactic plane. In the universe at large, there is no natural choice at all. This isn't just a philosophical point. It has real, practical consequences. When astronomers map the universe, they have to choose a coordinate system. And different systems reveal different aspects of reality. Ecliptic coordinates show the solar system's structure, but obscure the galaxy. Galactic coordinates reveal the Milky Way, but hide the ecliptic. Each coordinate system is a lens. None is more fundamental than any other. The fact that the ecliptic is tilted 60 degrees relative to the galactic plane means that the solar system's above and the galaxies above point in very different directions. If you define up as perpendicular to the ecliptic and travel in that direction, you'll be heading at a steep angle through the galactic disk, not straight out of it. Conversely, if you define up as perpendicular to the galactic plane and travel that way, you'd be heading at a steep angle relative to the solar system's ecliptic, not perpendicular to it. The two reference frames don't align. And this misalignment is a vivid illustration of the fact that above is not an absolute concept. There's another layer to this. The Milky Way itself is moving through space. Our galaxy is part of the local group, a collection of about 50 galaxies, and the local group is part of the Virgo supercluster, which is part of an even larger structure called Laniakea. All of these structures are moving relative to each other and relative to the cosmic microwave background. The Milky Way is falling toward the center of Laniakea at about 600 kilometers per second relative to the cosmic microwave background. This motion defines yet another direction, a direction of travel that has nothing to do with either the ecliptic or the galactic plane. If you chose this direction of motion as your reference, defining forward as the direction we are heading, and up and down relative to that, you'd get yet another orientation. The concepts of above and below would shift again, pointing in yet another direction in space. And this reference frame would be just as valid as any other. There is no cosmic authority that decrees which direction is truly up. Even the cosmic microwave background, which fills the universe almost uniformly, has a very slight asymmetry due to our motion through it. Because the solar system, the Milky Way, and our entire supercluster are moving relative to the frame in which the cosmic microwave background is most uniform, we see a very slight blue shift in the direction we're moving and a very slight red shift in the opposite direction. This dipole pattern defines a direction in space, but even this is relative to the rest frame of the radiation left over from the Big Bang. Change your motion, and you change the dipole. The conclusion is inescapable. There is no absolute up or down in the universe. There is no cosmic ceiling above our heads. There is no cosmic floor beneath our feet. There are only reference planes, chosen for convenience, each one defining its own version of above and below. The solar system's ecliptic gives one answer. The galactic plane gives another. The plane of the local group, the plane of Laniakea, the dipole of the cosmic microwave background. Each gives a different answer, and none is more correct than any other. This realization is disorienting. We're creatures of gravity. We evolved on a planet where down is always toward the center of the Earth, and up is always away from it. These directions feel absolute, unchanging, universal, but they're not. They're local. Step off the planet, fly away from its gravitational influence, and those directions lose all meaning. In space, you can orient yourself however you like, and every orientation is equally valid. And yet, this lack of absolute direction doesn't diminish the structures we've explored tonight. The solar system really does have a flat inner region where the planets orbit near the ecliptic. It really does have a thicker outer region where Kuiper belt and scattered disk objects orbit at steep inclinations. It really does have a spherical Oort cloud surrounding everything, and it really does sit inside the Milky Way's disk, tilted at 60 degrees to the galactic plane, bobbing up and down through it over millions of years. These are real physical structures with real physical shapes. The fact that there's no absolute above or below doesn't make the structures any less real. It just means that describing them requires choosing a reference frame, and different reference frames highlight different aspects of their geometry. Let's bring it all together. We started with the flat diagram of the solar system, the picture every schoolchild knows. 8 planets orbiting the sun in a neat disk. We asked a simple question: what lies above and below this disk? And the answer turned out to be far more complex and far more extraordinary than anyone expects. At the smallest scale, even the flat disk isn't perfectly flat. The planets have small orbital inclinations that take them millions of kilometers above and below the ecliptic. The asteroid belt contains objects with inclinations up to 35 degrees. The solar system's flatness, even in its inner regions, is approximate, not exact. Beyond the planets, the Kuiper belt and scattered disk contain objects with inclinations up to 45 degrees and beyond. These objects orbit far above and below the ecliptic, occupying a thick donut-shaped region that the flat diagram completely ignores. Some objects even orbit in retrograde, going around the sun backward and at steep angles, proving that the solar system contains orbits at essentially every possible orientation. Beyond all of these, the Oort cloud surrounds the entire solar system in a vast spherical shell stretching more than a light year in every direction. Above the ecliptic, below the ecliptic, to the sides, there is no preferred direction in the Oort cloud. It is the same in all directions. The solar system, at its largest scale, is a sphere, not a disk, and the flat picture that lives in your head shows only the thinnest innermost layer of the sphere. Zooming out further, the entire solar system sits within the Milky Way galaxy, tilted at 60 degrees to the galactic plane. The sun bobs up and down through the galaxy's disk over tens of millions of years, carrying everything with it. Above and below the galactic plane lie the stellar halo, the dark matter halo, and eventually intergalactic space. The structures keep getting larger, and at every scale, the concept of above and below shifts depending on which reference plane you use. And ultimately, there is no absolute above or below. These directions exist only relative to chosen reference planes: the ecliptic, the galactic plane, the cosmic microwave background. Each defines its own version of up and down. In the universe at large, all directions are equal. There is no ceiling. There is no floor. There is only space stretching out in every direction, filled with structures at every scale, from the tiny disk of planets at the center of our solar system to the cosmic web of galaxy filaments spanning billions of light years. The flat diagram lied to you, not intentionally and not completely. It showed you something real about the inner solar system, the thin disk where the planets orbit. But it hid the vast three-dimensional reality that surrounds that disk. It hid the tilted orbits of the outer solar system objects. It hid the spherical Oort cloud. It hid the galactic context. And most profoundly, it hid the fact that above and below are not absolute truths, but human constructs, convenient references that we impose on a universe that has no preferred direction. The next time you see that familiar flat picture of the solar system, you'll know what it's not showing you. You'll know that above and below those neatly arranged planets, stretching for more than a light year in every direction, there are trillions of icy objects forming a vast invisible sphere. You'll know that the solar system is embedded inside a galaxy at a 60-degree tilt, bobbing up and down through the galactic disk. You'll know that beyond the galaxy lie the halo, the intergalactic void, and eventually other galaxies and larger structures stretching to the limits of the observable universe. And you'll know that none of these directions, above or below, up or down, is more fundamental than any other. They're all just perspectives, ways of orienting ourselves in a cosmos that has no inherent orientation. There's something beautiful about this. We're creatures who need up and down. We need the ground beneath our feet and the sky above our heads. These directions are wired into our biology, into our sense of balance, into the very structure of our inner ears. We can't help thinking in terms of above and below. And yet, when we look honestly at the universe, when we follow the question of what lies above and below the solar system to its ultimate conclusion, we discover that these directions dissolve into nothing. The universe doesn't have an up. It doesn't have a down. It just has space, vast, three-dimensional, extending in every direction without preference or hierarchy. And somehow, in one thin, flat disk, within one spherical cloud around one ordinary star, in one galaxy among trillions, a small, rocky planet formed. And on that planet, creatures evolved who could look up and wonder what was above them. The answer, as it turns out, is everything and nothing, and the same thing in every direction. The universe surrounds us equally, above and below, in every dimension, at every scale. And we're here in the middle of it all, trying to make sense of a cosmos that has no middle, no edge, no top, and no bottom. Just an endless, breathtaking expanse that we call home. If you found this exploration meaningful, a like or subscribe really does help this channel grow. And the next time you look up at the night sky, remember, you're not looking up. Not really. You're looking out in one particular direction from a small planet in a vast spherical solar system, inside a galaxy that has its own definition of up and down, floating in a universe that has no definition at all. There is no above. There is no below. There's only the cosmos, and you're part of it.